my talk here is to show you a cute, or at least a cute proof, or at least I think that it is cute. And this is joint work with Yuval Perez, and the topic is uniform spanning trees. So let me just tell you just the basic setup. So we have, we're always going to have a finite connected graph. And when you have a connected graph, it has a finite set, a finite connected graph, you have a finite set of spanning trees. So spanning trees, just in case this is not known to you, the definition is, I think about it just as a collection of edges, a subset of edges of the original graph, spanning trees of G. It's a subset of edges touching all the vertices, touching all vertices, and containing no cycles. So it's a tree that touches all the vertices of the graph G, and no cycles. Right. So this is a finite set, and I will write usually UST of G for either the probability measure, which you get by sampling one of these trees uniformly at random, or just for a sample from this set. So this is a uniformly drawn spanning tree. And I'll try not to give you a history of this model. This is a very popular model in probability, combinatorics, statistical physics, and it is actually known how to sample these things or how to enumerate these things. This is Kirchhoff's theorem that we will see again, I guess, that everyone here has seen before, that gives you a quick way, given a graph, how to at least count these trees. Do you require the spanning tree to be connected? Right, excellent point. This has to be connected, right? Thank you. Yeah, otherwise it could just be some kind of a matching. Thanks for this point. Where was I? There are many ways of sampling such a thing, such an object, Wilson's algorithm, or Aldous Broder algorithm. There are many studies of this object in the infinite graph setting, and it's a very interesting model, or the way Rick Kenyon says, it's a which I like. It's one of the great heroes of probability theory. So I'm going to tell you a little bit. So I'm not going to tell you much about the history. I'm just going to state one theorem and try to give you as much insight to the proof of it as I can. So here's the theorem. I'm interested in, so I have a graph or a sequence of graphs. I'm drawing uniform spanning trees, and the object that the quantity that I'm interested in is, for instance, the number of leaves, or perhaps, so a leaf is a vertex of degree 1, or perhaps the number of vertices of degree 2, or perhaps the number of vertices that the ball of radius 2 from them looks like this. For instance, right? What is the frequency? How many of these objects do I see in my tree, right? In the uniform spanning tree that I choose. So here's the theorem. I will tell you. I will first write the theorem. Perhaps not everything will be clear, and then I will explain to you what it is. So we have a sequence of finite, simple, connected graphs. Connected. I guess I should put commas. Connected regular graphs. By regular, I mean that all degrees are the same, right? They're all equal, and the degree, all regular degrees, let's say d of n, and I'm assuming that the degrees are high, just tending to infinity in any rate that you would like. You have such a sequence. You can take any particular sequence that you like. It could be the complete graph, hypercubes, anything you can build. Obviously, there is an abundance of such objects. And now let's denote by forget what this letter is. Is it delta? Is it rho? It's one of them. So let's just call it rho n. Rho n, is it not rho?
Gamma.
Gamma. Yes, my Greek is so-so. Even though I am a quarter Greek, I have to admit. Gamma n is the uniform spanning tree of Gn. then the local limit, I will tell you more or less what it is. The local limit of gamma n is a Poisson 1 Galton-Watson tree conditioned to live forever, conditioned to survive. And instead of defining to you formally what is a Poisson 1 Galton-Watson tree conditioned to survive, let me just tell you how you sample such a thing. And then I will also, instead of telling you what is a local limit, I will just tell you, what kind of things you can compute from this theorem, and then it more or less should be clear. So a Poisson 1 Galton-Watson tree conditioned to survive. Well, I kind of said what it is, but let me tell you of a nice way of sampling it, which perhaps all of you know. So this is just an infinite random rooted graph. And here's how you sample it. You start with an infinite one-directed path. Sorry, so you start with a fixed deterministic path. The bottom vertex is the root, which I guess this is the letter rho. So this is okay. Thanks for nodding. And on each of these on each of these vertices, I hang an unconditioned Poisson 1 Galton-Watson tree, which everyone knows, of course, is a finite object. So here all of these. So this is the limiting infinite graph that I get when I look locally on the what was that letter again? Gamma n, the UST of Gn. And what does it mean? It means that if I choose a uniform, so if I want to, so x, if I look at x, a uniform vertex of Gn, right? R is some fixed integer, right? And I look at the random variable, the ball in gamma n of radius r, the ball in the graph distance of around a random vertex. So I think about this as a random variable taking values in the space of rooted finite graphs, right? So this converges in distribution in this space to the ball in this Galton-Watson tree, so Poisson 1 Galton-Watson around the root of radius r. So for instance, what this theorem tells you, that if you start from a sequence of regular graphs with degrees tending to infinity, let's just think, for instance, on the hypercube, if you want, just as an example, or the complete graph. So for instance, the corollary that we get is that the number of leaves is asymptotically, right, with high probability, it's going to be, right, the leaf, right, you have to have a Poisson, right? So what is the probability that the root is a leaf in the Poisson 1 Galton-Watson tree, just by the way I described to you the construction? So you have to have that the first, right, the first progeny of the root, right, on the unconditional tree hanging on it, it has to be 0, right? So you have to have a Poisson 1 random variable to equal 0. That is some people say 1 over e. Right, so this will be n over e plus lower order terms with high probability, right? Or let's take something more complicated, right? The theorem tells you all of these finite structures you can calculate exactly. If you want to compute the number of vertices such that, let's do something slightly more complicated, right? So this is r equals 2, and you want to say what is the probability that you see this object, not when x is chosen, when the uniform point is chosen randomly, or alternatively, what is the frequency of this structure? Then you look at just the corresponding Poisson 1 Galton-Watson tree. So here you look only at this tree up to height 2. So you don't, from looking at this tree, you are not sure which is the infinite path, right? So the question that you ask yourself, what is the probability here in this tree? What is the probability in this Poisson 1 tree? What is the probability that you look like that? But when you just see this picture, you don't know where was the infinite path. So you have to, of course, take the two options into consideration. These are disjoint event, right? And then so assuming that this was here, assuming that this is the infinite path, I'll already write the 2 because, of course, the other side will be symmetric. What is the probability of seeing this? Then I have to have, right, I have to have one progeny coming from the root, right? And this costs me 1 over e, right? And I have to have 0 progeny coming from the vertex right there, and 0 progeny from here, right? So this will be 1 over e cubed twice for the 2 choices, and I don't know anything about the 2 vertices at the top at level 2, right? So this is one thing that the theorem gives you. The frequency of appearances of these precise subtrees is this, no matter what was the underlying graphs that you have started with. So let me write to you, just to make it clear, let me write to you, if I give you, okay, so I did this calculation for two particular small subtrees, right? Leaves and this picture. Let me just give you the formula. If you're giving me a finite fixed rooted tree, how do I calculate what is the frequency of it? So it's just a formula. And the formula, in fact, is, of course, equivalent to the theorem, right? If I tell you what the formula is, then this tells you what the local limit is, and you can compute to yourself that the formula that I tell you is, in fact, the probability of seeing these trees in the Poisson, Galton, Watson tree. So here's an alternative formulation. Which is sometimes easier, sometimes it's more confusing. So T is a fixed rooted tree, height R, and TR is the set of vertices of T of distance R from the root. Right, the fixed tree T is a rooted tree. It comes with a root from root. Right, so there's one more quantity that for the formula that I have to keep in mind, and this I'll just call it stabilizer of T. This is just the set of graph automorphisms, whatever, let me not embarrass myself by spelling it, T to itself, fixing the root. Right, so for instance, in this graph, you can, in this graph that I've just plotted to you, you can see that the size of this automorphism is just 2, right? It's just, you can just flip the two sides around. And now I can restate. So now the statement is the probability that when I look at the ball around the uniform spanning tree, centered at a uniform vertex X, so I'm reminding you that X is a uniform vertex of Gn, right? You look at some neighborhood R, and you ask yourself, what is the probability that this is your some fixed tree T with these parameters TR, stab T? Then there's a formula, here it is, T of R. So you just, this is just the number of vertices at the top, divided by the size of the size of the automorphism group that preserves the root, and exponent of the number of vertices of T minus the size of the top level. Right, so for example, if we look at this example again, right, as I said, the stabilizer is 2. Right, what is my problem here? Seems like 2 is seems like there's some problem, right? Interesting. Okay, let's not look at this example then, and put a question mark here. I guess I may have made some error either in the calculation here or in the formula here. It will not matter for what I'm about to show to you next. I just wanted to convince you that there's a formula. Turns out that it could be incorrect, but one way or another, I will show you the proof, and the formula will come out. let me just say some words of history. So this for the particular case when Gn is Kn, this is a very classical, beautiful theorem due to Jeffrey Grimmett from, I forget if it's from 80 or 81. So this is what he proved, that when you look at the complete graph, and then in fact the tree that you're choosing is just a uniformly chosen labeled tree on n vertices from the set of n to the power n minus 2 trees that you have, right? So this theorem is and of course the Grimmett's theorem is a particular case of our theorem. So this is one thing, and so this is one past result. So the background is going to be very short. And one point, another thing that I should mention is if dn is linear. If dn is linear in n, then actually this is known. This is a corollary of a theorem that I proved together with Honza, Jan Daki, myself, and Tuan Tran from 2018, or perhaps it was 17. And there's something special about linear degrees because it allows you to decompose the graph into finitely many expanders. So there's something definitely easier happening there that I will try to allude to. But when d can grow, as long as it grows to infinity, but could grow extremely slowly with n, there's no such known partition theorems for your graphs that are strong enough to get such a thing. So some new approach or a different approach is needed. In fact, it turns out that a very old approach is doing it, and the proof relies on some electric networks and a deep theorem of Kirchhoff from the mid 1800s. So this is definitely the oldest theorem that I use as modern theorem that I use in my research. Are there any questions before I start telling you some words, some things about the proof? So feel free. Well, I guess you can't really stop me, but feel free to try to stop me, and I will answer any questions that you may have. So the proof relies on electric network. I never know if this is a standard material because I didn't learn it as an undergrad. So it will definitely, if you have never seen it, this could be a little confusing. And even if you have, this is still a confusing things. And I hope that I will at least, if not more, at least arouse your curiosity about this wonderful tool, and try to convince you that it is deep and has a lot of uses and probability. So here is the starting point, and this is a theorem due to Kirchhoff in a very influential paper from 1847. Right, so this is Kirchhoff. And the theorem is the following. You ask yourself, and it's actually it's a theorem that is so we all know perhaps that the more familiar theorem of Kirchhoff that relates to spanning trees is the enumeration of spanning trees. We all think this I think is standard. If you have a connected graph, you can calculate the set, the size of the set of spanning trees by considering a determinant of some matrix, right? And the matrix is the Laplacian matrix, where you take a minor out of it. And this theorem that I'm about to write you is actually equivalent, even though the equivalence is not immediately seen. And so it does not count the number of spanning trees directly. It computes the probability that a particular edge in your graph is in your spanning tree. For instance, whatever this theorem is, it should make sure that if I have an edge like this, xy, right, that separates the two parts of the graph, an edge like this has to be in the spanning tree, so it better be 1 in whatever I'm about to write. So here's the theorem. G is a connected graph, connected finite graph, and everything here is going to be finite from now on, or from the beginning. You have an edge xy in your graph, and you're asking yourself, what is the probability that this edge xy belongs to the uniform spanning tree of G? And it turns out that this is exactly the effective electric resistance between X and Y. And this, so what is effective electric resistance has many definitions, but we will mostly be thinking about it intuitively in the terms of high school physics. So you think about your graph as a electric circuit, and you release unit current flow from X to Y, right? And I'm reminding you, Ohm's law, right? I always have to remind myself of this, right? That V, the potential difference, equals the amount of current flowing times the resistance of the circuit from X to Y. So the resistance, if I send a unit current flow from X to Y, and I look at the potential difference that it induces, that difference is the effective resistance. Or alternatively, right, I could put a battery on one side, the minus on X, the plus on Y, and assume that this battery, and fix the battery to have voltage difference 1. And I look at the amount of current flowing from X to Y, and the inverse of that is the resistance. So you see that in this particular graph, it immediately, you can see that it is 1 because electricity will not go into the other graphs on both sides, will just flow directly from X to 1. You will only have 1 going in this, and there is no electricity going on the other sides of the graph, right? So this will be 1, and you can also convince yourself that because we started with an edge and not just any two vertices of the graph, then that this number is always smaller or equal to 1, right? Because if there's an edge there, then of course electricity could just take that edge and flow directly on this edge, giving you resistance 1. But of course, we already have the physics, the high school physics feeling that the electric current chooses the most efficient way of spreading the weight. So this may not be the optimal weight, but because it's no more than that, then this number is no more than 1. Okay. And the proof, so let me start with, so this is the basic theorem that we will rely on this proof. And the proof does not rely on more advanced tools, such as Wilson's algorithm or other sampling algorithm. We really just use this. And in case you haven't seen the proof of this is very nice. And I highly recommend, there's a cute combinatorial proof showing this. In fact, there are several proofs. Let's start with a simple observation, and then I'll tell you what is the heuristic of the proof of the theorem. So here's an observation. If I have if I have two vertices in your graph, two distinct vertices in your graph, X is different than Y, then the resistance, the effective resistance between X and Y is always at least 1 over the degree of X plus 1 plus 1 over the degree of Y plus 1. And let's see why this is true. And again, this is the same intuition that the electricity flows in the most optimal way, right? So if this is X and this is Y, let's assume for the moment that there's no edge between them, right? So let's assume that there's no edge between them. Then optimally, the electric flow, had it been optimal, it will divide all the flow, all the 1 that goes just into its immediate neighbors equally to every neighbor. So you will have 1 over d of X flowing on this every edge. And on the other hand, to enter Y, it will come to Y from all of its neighbors equally. This would be the best scenario. And in this scenario, you can immediately check by this, by computing the voltage, that you get something like, in fact, if there's no edge between X and Y, you can remove this plus 1. Right? This, of course, will not be material for us because we are in the setting where the degrees are high, right? So this should be the same thing, right? So in general, when you're in so what this means is when you're in if Gn are Dn regular, right, and Dn goes to infinity, this means that the resistance between any two vertices is always at least 2 over d asymptotically, right, up to the constant. But of course this is not sharp, right? Because we saw an example here that you have an edge that has resistance 1, right? And 2 over d, of course, is a very small number. So how do you deal with that? You would like to argue that somehow for most edges or for most pairs of vertices in some random way that I haven't quite told you yet, this is the right thing to obtain. That there is actually a corresponding upper bound. Of course, this is not true as I said it, but let's just for the heuristic assume that it is true, that we have a corresponding bound. So let's for the heuristic. In fact, you can prove when your graph is an expander or the random walk mixes very well, you can actually show directly that this will hold for any pair of vertices. And this is what the work that I mentioned earlier with Jan Haldaki and Tuan Tran actually relies on, because you know that most places of your graph look like expanders, then you have such an estimate, the converse of this estimate. So heuristically, let's assume I'm not kind of exactly telling you what I'm assuming, but let's assume that we have for all vertices, for all pairs, for all xy, I will only use it for edges, but I can assume, as long as I'm assuming something that is not true, let's just assume for all let's just assume it for edges. Assume that for all edges, the effective resistance between x and y is really 1 over the degree of x plus 1 over the degree of y times 1 plus little o of 1. Okay, now in this assumption, I'm particularly writing dx and dy. I'm not writing degrees anymore because that's 2 extra letters and I'm lazy. Because I will want to consider cases in which the graph is not regular, as you will see right now. But still, it will be the case that these degrees are high, right? So what do I do? So let's try and take prove heuristically this particular case. I found a case that both the formula that I've shown you and the theorem seem to agree. So this will be easy. Let's look at the case. What is the probability or what is the frequency of a path of length 3? So I mean a vertex, the vertex rho sees in a ball of radius 3 a path of length 3. This is what we're trying to compute. Okay, once I explain this heuristic, it will be more clear why am I showing you the rest of the proof. So let's try and do that. So firstly, I would like to, so I'm trying to compute this probability. So of course, I have to choose this path of length 3 in my regular graph, and I have approximately number of such paths. Starting from rho, paths starting from rho is approximately, of course, from rho is approximately d cubed, right? In fact, it's d cubed times 1 plus little o of 1, right? This is just the number of choice. So now that once I fix this choice, so now let me write perhaps rho v1, v2, v3. Now these are particular choices of vertices in your graph, and I'm asking, so the probability that I'm trying to calculate in the UST is what is the probability that all of these 3 edges are in the UST and all of these edges are not in the UST. All the other edges emanating from rho are not in the UST. All the edges emanating from V1, except for the edge V1, V2, is not in the UST, and the same thing here, right? So I have 3D pairs of edges that I have to make sure are close. So now let's do this heuristic heuristic calculation. Let's start with calculating the probability that this path is open, right? That this is in the UST. So we do it sequentially, right? We start with the first edge, or let's just do it, right? V1, V2. What is the probability that it is open, right? So by Kirchhoff's theorem, I just explained to you if I look at one edge, what is the probability that it's open? It's the sum of the inverse degrees, right? If we started with a regular graph, then I will just get 2 over d, right? This is the probability that this particular edge is open if you believe if you take as granted this assumption. Now, conditioned on V1, V2 being in this UST, what is the probability that V2, V3 is in the UST? right? So you have to forgive my calligraphic style, right? What is the probability? So this is a known fact about uniform spanning trees. If I condition on an edge exist, and I want to choose the uniform spanning tree, condition on some edge being present in this uniform spanning tree, then what I do is I just shrink this edge, identify its 2 points, right? I don't erase any other edges, right? So now perhaps my degree of this new vertex is much higher. I contract this edge, draw a uniform spanning tree on what's left, right? And then open back this edge, and what I get is a uniform spanning tree condition on this edge being present, right? So once I contracted V1, V2, right? So now I have a vertex which is both V1 and V2, right? And I have a V3, right? And I'm asking, what is the probability that this edge is open, right? And now, if you again believe my assumption again, so now the degree of this vertex is 2D, right? And the degree of this vertex is D, right? So we get, so we had 2 over D, and now we're going to have 1 over 2D plus 1 over D, and some people say that this is 3 over 2D, right? So now, now I do the same thing again, condition on the edge V1, V2 to being in the uniform spanning tree. I contract them, and I ask, what is the probability that V3, V4? Sorry, and now I see that I had a row V1, V2, V3. So let's just instead of erasing, I'll just write V1, V2, V3, V4 to make it especially confusing to the people who just started listening to me. So now it's the same deal, right? We have shrunk V1, V2, V3. We have a vertex of degree 3D, and the fourth vertex has degree D, right? So it will be 1 over 3D plus 1 over D, and this is 4 over 3D, right? And of course, I have to multiply all these numbers, right? And I also have, of course, this everything I'm drawing a circle around, I will eventually multiply, right? Everything that I'm doing here is conditional. So, but of course, this is not the end, because I also have to make sure that all of these edges are closed, right? So let's do this calculation, right? So now, after I condition on the path being V1, V2, V3, V4, being in this V1, V2, V3, V4, being in the uniform spanning tree, I contract it all. Now this vertex has degree 4D, right? Because I have 3D from V1, V2, V3, right? 3D from the first three, and another D from the fourth, right? So this will be D vertices, D vertices, D, and D. And I have to calculate the probability that the first 3D edges are closed. So let's see, what is this probability? So the probability that 3D edges are closed, right? I have to work sequentially, right? Because I can't do it all of them together. I have to close one by one. So let's assume now I have this giant vertex, 1, 2, 3, 4. And let's assume that I have closed already I edges. So I'm conditioning on the fact that they are closed. And I'm looking now at this new vertex here, right? Its degree is D, or it could be a little smaller than D. So here I'm again massaging the argument. So let's assume for the moment it is D, and the degree of the vertex. So this vertex has degree D, and this vertex has degree right. So it will be 4D minus I, right? And so that's all you need to know. And I want this edge between the two to be closed, and I have to take the product over all I. I goes from 1 to 3D. So let's write this this product, I from 1 from 3D, 1 minus the probability that it's open, and that we already know by our assumption is the sum of the inverses of the degree, right? So this will be 1 over D minus 1 over 4D minus I. Let's estimate this calculus 1 kind of way. Right, so this will be e to the minus sum I from 1 to 3D of 1 over D minus sum from I to 3D of 1 over 4D minus I. Great. So this, of course, is equals 3, right? So it's e to the minus 3. And this sum, right? This is the sum of 1 over k, right? K going from d to 4d, right? When I is 0 or 1, it is 4d, and when I equals 3d, this is just d. So this is just going to be the logarithm of 4d minus the logarithm of d, right? And they say, some people say that this is 1 over 4, right? There's an e to this power with a minus. I get here a 1 over 4. So this is the fourth or fifth term that I need to multiply. I multiply all of these together. The power of d, the d cube here cancels all the d's. I get that the probability is 2 times 3 over 2 times 4 over 3 times e to the minus 3 times 1 over 4. And voila, we get e to the minus 3. Okay, so at least for this particular example, we have verified both the formula and the theorem, right? And you can imagine that this is just a recipe for doing it for any particular graph. You can write down a formula if you believe this assumption. So this is how you derive the formula that I wrote here. This formula. Okay, so we see that the statistics of edges in which a bound like this holds, a bound of this form holds, is actually very important, and this is what we want to use, right? And for here, so we are asking ourselves the first question is, right? This number usually is small. How many edges? How does it spread? And it turns out that for this, there's a very elegant, nice theorem known as Foster's theorem. Foster theorem, which for us now it will be immediate if you believe Kirchhoff's theorem, and this is the theorem for any connected graph G. If you sum over the edges x, y, I don't mean order edges. If you sum over the edges of the graph the pairwise resistance between x and y, what should you get? Oh, I forget that there's no speakers, right? I know. Let me tell you what you get. You get right, because this is Rxy is the probability. This is over the edges. Xy is the probability that the edge is there, but we know that the total number of edges is exactly n minus 1. So I get here n minus 1, and this is it, right? This is the sum. But so we can restate this. So let's restate this. Right? If I look at the expected effective resistance between x0 and x1, where x0 is uniform, right? And x1 uniform vertex of G, and x1 is a uniform neighbor. Right? So this is really just choosing a random edge, right? So this expectation, right, just turns out to be right. The number of edges is dn over 2, right? The total number of edges is in a regular graph is dn over 2, right? So I just take this sum, divide it by this, and I get something like 2d plus 1 approximately that, right? This is what the statement says. But notice that we also have a deterministic lower bound. A deterministic bound, right? For any two vertices, right? For any edge, Rxy is always bigger than 2 over d times 1 plus little o of 1, right? So it's a random variable that is deterministically bounded below by some small number, 2 over d, and its expectation is of the same order. That means you cannot have many edges that violate this bound, right? So this is the first ingredient that you see here. So let's write the corollary without the proof. Again, the proof is just counting, right? So the number. Let's not even write down this corollary. The corollary is most edges xy have the resistance between x and y is of order 2d 1 plus little o of 1. right? So this all fits what I was trying to tell you, that this is the assumption, right? So I of course I can't say it for all edges. I have it for most edges. So this is of course this is very easy, but now let's take it one step further. Foster's theorem was known, actually, you don't have to use Kirchhoff's theorem. Let me tell you our first variant of Foster's theorem. So this is a lemma. Here's a lemma, right? So I'm looking at a Foster's theorem restated like this, right? You choose a random edge or a random vertex, and then taking one step of the simple random walk. What happens if you, as you see from this example, right? I don't have one, right? And I'm taking random walks because eventually I'm enumerating over the graph structure, right? Over the tree structure. So I want to take longer random walks. So let's take let's say x nod is a k-step random to xk is a k-step random walk, right? Starting from my uniform, x nod is uniform, right? Then the lemma says that the expected resistance, then the expected electric resistance between x naught and xk is also of order 2 over d. Right? So this is an extension, right? Because it tells you not only a random edge, but also if you take the endpoints of a random path, you will also get this 2 over d. And let me try to show you the proof. The proof is cute. And let me try to even show you the proof in the case that you already know, which is the case k equals 1, right? So this we already know. But let me show you a different proof of Foster's theorem that will be that is nice. So proof for k equals 1, even though we already know it, but it's a different proof that will work. I will leave you the details of how it works for higher k. So I fix a vertex x nod, right? This is not a random vertex. This is just a fixed vertex x nod. And I'm looking at the expected time for the random walker starting from x nod to return to x nod. X nod, this is a fixed vertex. So this is the expected return time. So we know, right, in any irreducible Markov chain, right, the expected return time is exactly the inverse of the stationary measure, right? So that means since the stationary measure for this is a regular graph, right? The stationary measure is 1 over n for every vertex. So this is just n from general Markov chain theory, right? So let's write this. So let's just condition on the first step of the simple random walk, right? X naught tau x naught plus. So this is just 1 over d, right? I'm going over all of the neighbors of x naught and asking myself what is the expectation when I start from x1. How long it takes me from a random neighbor to return to the origin. And of course, I have to add 1 because I just took one step from x naught to x1. But on the other hand, right? If I on the other hand, what is what is the expectation of the expected return time from x1? Now x1 is a uniform neighbor of x naught. So I choose a uniform neighbor and ask myself, how long does it take me to return? Right. So it's almost the same quantity. And here I don't need the plus, right? Because it's a different vertex. I assume that the graph was simple. Even though it doesn't really matter for this proof. So this is the same thing, right? Here I'm just writing this. So this quantity is just 1 over d times the same sum, right? But without the plus 1, right? But the plus 1, right? The plus 1 cancels with the 1 over d, so you get that this has to equal n minus 1. Okay, but what we've learned is that what we get is that is that if I look at the expectation of this quantity, so now x0 is a uniform vertex, right? So is this equality is where I used is just where I use this, right? Because I have the same thing written except for this one that I've removed. So what we get is that this equals n minus 1 when now both the starting point x0 and x1 are chosen at random. Right, but because of reversibility, of course, I could look at the graph at the random walk starting at x0, taking one step, but it's the same thing as like looking at that step and moving backwards, meaning that this equals the this quantity, obviously. Right. So what we get is that the expected commute time, right, the expected time to go from x0. So this is x0 to x1 plus the expected return from x1 to x0, that this is 2n minus 2. Right? This is exactly what we need. And this, I'm reminding you, the commute time is directly proportional to the effective resistance, right? This, for fixed x1 and x0 and x0 and x1, this is exactly twice the number of edges times the resistance between x0 and x1, right? So, and I know, of course, the number of edges, I divide and I get exactly what I want. So the lemma goes, of course, by doing the same kind of trick, but instead of conditioning on the first step, you condition on the first k steps, and you collect all the errors that you get here, and you do the same kind of manipulation, and you get exactly this lemma. Right, so now comes the point that I will try to convince you with some hand waving. In the calculation that we did for the heuristic, actually we throughout this, because we condition on some edges occurring or not, we actually needed to compute. If you look at at what we did at every step, we needed to compute the resistance between 1 point and 3 points. Right, this was the calculation, for instance, that we did here. We computed the resistance between V4 and the union of V1, V2, V3, right? And we got that this is this number. So this is still, so this is our second variant of Foster's theorem. Let me tell you what it is. So lemma 3, and tell you just with a bit of hand waving how do you prove it. So now I have the same thing. X0 to xk is a k-step random walk, right? And I'm looking at the resistance between xk and x1. Sorry, so I'm sorry for this, but it will be easier for me to start this time the random walk from 1 instead of 0. Right? And again, x1 is a uniform vertex, and I'm looking at the resistance between the last vertex and all of the past. So this time it's not actually immediately clear what the answer should be, but the answer should be k over k minus 1 times d 1 plus little o of 1. And this actually holds with high probability. Here I told you, in this lemma, it was a resistance lemma, but because you have the same deterministic lower bound, you also get that this holds for most 2 points x0 and xk. But these are not, again, random points. These are 2 points that you get by choosing a k-step random walk. So this is a different estimate that you have here. So let me tell you just what is the idea of the proof, and I will finish by this. Right, you have a random walk, right, and you have the last point, but you know, because of the previous lemma, you know, right, you know. So the proof is you know that the resistance between xi and xj is approximately 2 over d, right? For any, with high probability, for any I, for any two time differences, for any ij, you look at xi and xj, the path between them is just a simple random walk starting from a uniform point. So you can apply the previous lemma and you get exactly this with some errors. So now you come to a question. You have a network, you have some large graph, and you have inside k vertices such that the pairwise resistance between any two of them are approximately the same number, right? So you have so you have k points, right? 1, 2, 3, right? A part of a large network, and you would like to know, right? And you would like, so you know the pairwise resistances, but what you would like to find is the resistance between one vertex and the rest of the set. And you can ask yourself, is this even determined just by knowing the pairwise resistances? So turns out that the answer is yes. And in fact, if you do this, assume, for instance, if you assume that this is the complete graph and you can compute everything, then you can even guess this constant k times k minus 1. So it turns out that the answer is yes. And I will leave you with a little bit of curiosity as to why it is true. But it turns out that this is true. And the reason is that there's a well-known but a discrete form of the sentence that every probabilist likes. The inverse of the Laplacian is the Green's function. And if you think about this sentence long enough, then you realize that one particular corollary of it is a statement of this form. I hope you enjoyed this proof, and I thank you for your time.
Thanks very much for a beautiful talk, Asaf. I'm going to invite people to ask questions by putting things in the chat. I know that Alex has one. I'm just going to start by asking one. You mentioned in your earlier work that in the case where the degree is linear, there was something which was made easier by being able to decompose into expanders. Could you say just a little bit more about that?
So by decompose into expanders, as perhaps some of you guessed, because I think that this is also some combinatoric seminar, not just right. So this, I mean, Semiretti's regularity lemma, right? It tells you exactly this. And in fact, the work from before does not rely on, or does not assume that the graph is regular. A regular graph is just one particular example. So yeah, so there, Semiretti's regularity lemma allows you to decompose into regular expanders such that the amount of edges between the expanders is negligible. So you immediately get the same, if you choose a random edge, you're in an expander, and then you can show all of this. So in fact, this theorem is in some sense cleaner in the sense that Foster's theorem already gives you that. But of course, when it's not regular, then it's a different story, and then you have to think about what's really going on there.
Thanks. Alex, go ahead.
Yeah, so you had the assumption at the beginning that your graphs are regular. How much can you relax that assumption?
Yeah, that's actually a very good question that we've been pondering about, because so of course this proof is completely robust. So if for instance one thing that so it doesn't really have to be regular, it can be almost regular. So there's some function dn such that all degrees are dn plus some lower order error. So this definitely works, and our paper that will be published sometime soon contains this. But you know, it's a very legitimate question to ask. If I have some sequence of graphs, what can I say about the local limit of a uniform spanning tree? And it could be difficult, right? Because you could have giant degrees, right? In which all of the edges have to be present, right? Because this is a vertex that connects everything, and then they all have to be there, and then the limit doesn't even necessarily exist, right? Because this degree will be very large, so you don't even have any kind of tightness that we do here that I skipped. So I don't know how to answer it in full generality. This we just observe that this is a very, very, very nice, and we don't know a statement of this form that works in full in further generality.
Yeah, thank you.
Julian's next. Julian, you're unmuted.
Oh, great, thank you. Hi there. So I guess let me ask just a first question, which perhaps builds on Alex's question. Is so your theorem has the degrees going to infinity. I guess a very different behavior happens when D is bounded. I guess it can't be Poisson anymore, for example.
It will not be Poisson. In fact, you can get all sorts of very deep behavior. For instance, on Z2, right?
Right, exactly. Yeah.
Very hard to compute, right? Because it involves some discrete Z2 Green's function, has all sorts of crazy numbers. that Rick Kenyon and David Wilson compute, right? And degree, of course, it's no one knows. So in the bounded degree, it's a hard question, right? And the
interesting. Huh.
question there is to show that the limit exists, but describing it explicitly the way I did is very difficult on Z2. We do not know to give a description.
And so I just have another question too. I'm just trying to understand this result. So I guess how I'm interpreting it at the moment is you're describing the structure at a random vertex as well?
Yes.
Right. So is this sort of corollary that you used to illustrate, like doing like the ability to do all these counts? Is that essentially equivalent to the statement of the theorem?
This is also a very good question, and I thank you because it exposes what I was trying to hide from you, and that fact that there is right. So what Julian is saying. Oh, you sampled the point and told me that with high probability, but then you said, oh, but the frequency has to be that, right? So I was hiding a second moment argument, right? This, the answer to what this shows is just a first moment, right? The average, right? But there is a second moment argument that is actually not very hard because somehow parts of the tree, the uniform spanning tree, something that mixes very well in the ergodic theory terminology. So far parts of it does not have a strong correlation with from each other. So second moment is actually easier, and I was trying to hide it, but thanks for bringing it forth. So yes, there's an argument there that allows you from what I proved to you to obtain an almost sure frequency statement.
So that means sort of for almost all vertices you have this behavior.
That with high probability, the number of leaves is n over e times 1 plus little o of 1.
1 plus little 1, I see. Yeah, great. So would there be any chance of proving for, I mean, you might need something like, it's also D-connected or whatever, D-edge connected or something, but for all points, or I guess maybe you can screw things up locally for a given vertex.
So this relates to my previous comment. If you assume high connectivity, then you actually have other tools at your disposal because you understand the random walk much better, and you can prove something. You can indeed prove something stronger, right? But these kind of graphs can be very disconnected.
Right,
so
of course. Yeah.
Better connectivity, you have better control of the simple random walk, and this you can gain information from that.
Okay, thank you. Yeah, really helpful.
Thanks. Great. Well, there was one more question in the chat. I don't know, possibly you've answered it along the way, but maybe I'll ask it anyway. What's an easy example of a non-regular graph when the limit is not this conditioned, Golden Watson?
I can get, if you just look at I can give you an example where the limit doesn't even exist, right? You could just look at at a sequence of stars, right? If you look at if you look at stars, then the limit doesn't exist. But okay, you may say I'm cheating. So let me tell you a different example where I will not be cheating. Let's look at the complete bipartite graph, where on one side you have n over 3 vertices, and on the other side you have 2n over 3 vertices, and you put all the edges between them, right? So definitely not regular. On the left you have 1 degree, on the right you have a different degree, and it turns out that this is not a Poisson 1 branching process. And in the work from 2017 that I mentioned, you can show that this is a Poisson 1/2, Poisson 2 alternating branching process, conditioned to survive. Right. So each height it changes the progeny, depending on whether the height is odd or even. It changes the progeny distribution. Okay, so I think this answers.
That's great. Thank you very much. We're going to thank Asaf in a moment once I've stopped recording. And before I do, let me just say that at 3:30, so in just under half an hour, we'll have the second talk of the afternoon from Caroline Terry. And it just remains for me to press stop.